All right, so we're going to start with 17.1, and up until this point, we've been doing single variable calculus. And sometimes you need more than one variable when you're modeling a situation, especially in business. So we're going to talk about how to take partial derivatives, derivatives with x and y at the same time, different things like that. We're not going to go real deep into it, but we are going to go into it. So this example says the price of an item might depend on a lot of things. You might have to look at the time that it's been on the market. What are the competing items? What are the labor costs? What are the demands? So there might be several things that would affect the price of an item and what you would need to charge for an item. Bring that up a little bit. So because of that, we're going to work with some functions of several variables. And if you think about it, when you've done something with x and y, you know how to graph that. You know how to plot a point. If you're plotting 2, 3, you're over 2 on the x, and what do you do to get to the y? You go up on the y. But suddenly we may have 3 variables. So now we're going to be graphing in 3-dimensional. Oh, hello. So let's see. Here is an example of a business application. Real simple. Company's going to produce X items at a cost of $10 an item. So the total cost would be C of X equals 10X. Because we don't know how many there are, but they're $10 every time we have an item. Okay? Cost is a function of one variable, the number of items. But second part of that says the company produces 2 items, X of one item at cost of $10 an item, and Y of another item at $15 an item. So now to figure the total cost, we have to think about both of those things. So the total cost is a function of 2 independent variables, X and Y. In what we've done up until this point, it's always been X has been independent and Y was dependent on it. So you had one independent and one dependent. Now we've got 2 independent variables. Okay. Can I move up, or are we still right? So your total cost function would look like this. C of x comma y would be 10x plus 15y. So y is not dependent, it's independent, which is different than what we've had before. And then you might be asked to find, well, what's your total cost if you've got 5 of x and 12 of y? So that is a question saying, what is C of 5 and 12? Just like when we said with one independent variable, we would have C of 5 meant to plug 5 in. So C of 5 comma 12 means you plug in 5 for x and 12 for y. Do the operation, and you should get that the total cost was $230. Does that make sense? It's really not much different than what you've been doing. You just have to consider more than one variable as your independent part. And that's a real simplistic example of this. Okay. All right, so here's a formal definition of a function of 2 or more variables, and you don't need to write that down. You could have it if you print the notes. But the expression z equals f of x comma y is a function of 2 variables if a unique value of z is obtained when each ordered pair of real numbers that you put in. Okay? X and y are the independent variables. Z is the dependent variable. And this part right here, f of x, y exists is the domain, and f of x comma y, which would be z, is the range. So it's very similar to what we've talked about, a regular function in two variables, but now we've got, function of one variable. All right, so then we're going to do some evaluating of these, and here's the first one. If you were asked to find f of xy, where it was 4x squared plus 2xy plus 3 divided by y, and it says find f of negative 1 comma 3. What's it asking us to do? Just plug in negative 1 for x and 3 for y. So everywhere those occurred in the line, that's in red, where I've plugged in x here, I've plugged in x and y, and I plugged in y here. Okay? And you plug them in and you get a value. So f of negative 1, 3 would be negative 1. Okay. And so this is called f of xy, but you might also call it z. So if you were graphing on a three-dimensional graph, that would be your z. Okay. Questions on that? You're just plugging in. Same equation, find f of 2 comma 0. Now, what you should notice pretty quickly, if we remember our stuff from algebra, what's going to happen when we plug in 0 right here? It's undefined. So this point is undefined. It's not in the domain, because you would end up with 0 being on the denominator here, and you cannot divide by 0. So if we talked about the domain of f of x, y, that function we've been looking at, what would the domain be? Are there any restrictions on x? Just look up here. Would there be any restrictions on x? No. What's the only restriction on y? So it can't be 0. So the domain would be all numbers y not being equal to 0. So you sometimes have to think about that or look at that. And if either the x or the y are undefined, then it wouldn't be, the whole point would not be defined. All right. Here's one. Given f of x, y, z, now we've got something different. 4xz minus 3x squared y plus 2z squared, and find f of 2, negative 3, 1. And you're just going to plug in 2 for x, 1 for z, 2 for x squared, and negative 3 for y, and just plug in all the way, and you should get 46. So just make sure you could do that either by hand or by calculator, because you just need to get those values. Okay. Questions on that? We're just plugging in. Not bad. And now we're going to get to the graphing, and you will want to have one of these sheets. You didn't pick it up. Okay. Okay, so we're going to plot those 4 points that I have written up here, and I'm going to put them up here. I think maybe I don't know if we did 3. All right, and what you have to remember, and sometimes it gets a little crazy in your head, but x, when you're looking at the x part, this part to the left coming out, that's your positive part, and go straight behind it is your negative part. Okay, so it's this line right here, positive, negative. Y, positive is here, negative would be going back out here. Z, positive is here, negative is down here. And so when you're doing it, start at the origin and do your x first, and from there go to your y, and then go to your z. So if we are looking at this point here, let's do 1, 5, 4. Okay, so it's 1 on the x, so you're going to go here, that's 1 on the x. and then 5 on the y. So 1, 2, 3, 4, 5. There's not a dot there, but that's where we end up. And then 4 up on the z. 1, 2, 3, 4. Yes, sir. So this isn't difficult. It's just you have to kind of train your mind to think about positive is this way, negative is straight back. And this was, I looked all over for a grid that I felt was the easiest one to use. There's lots of grids out there. Some of them don't have the dots. They just have this. This makes it a little easier to count, and that's why I gave you that. Did Jahil question? Or John? Question? Uh-huh.
From the four from where you landed or 4 from the axis?
4 from where you landed. So you start here and you go 1 and then you go 5.
But you always count from where you landed?
Yes. Yes. Yeah, start with the X and start at 0, 0, 0, 0, 0 and go to X, then go to Y and then go to Z. Okay. Okay, what other point? I have 2, negative 4, 3. So let's try that. So that's 2 on the X. Now, negative 4 on the Y. Where's negative 4? That means we've got to go this direction, backwards, because here's positive. So if I'm at 2, then I've got to go, I'm trying to think, 1, 2, 3, 4, and then up 3, which would be 1, 2, 3. Does that kind of make sense? We ran out of dots and you can't see them. But we're 2 on the positive X, and then we have to go parallel to the Y. So negative 1, negative 2, negative 3, negative 4, and then up 3. So you're not going to have an axis to go along, but you got to go parallel to it in that direction, in the negative direction. Is that one okay? Okay. All right, now this one, 0, 0, 4, that's easy because you don't go anywhere on the X, you don't go anywhere on the Y, you go up 4. Felicia, did you have a question? Did y'all have a question over there? Okay. All right. Okay, 4, 7, negative 3 might be a little difficult for you because you don't have 7, but see if you can come up with it. It's not on this graph. See if you can do it. You're going to go 4 on the X, you're going to go 7 out this way on the Y, and then down 3. I don't know where that's going to end up, somewhere down here. 1, 2, 3, 4, and then 7 on the Y. 1, 2, 3, 4, 5, 6, 7. Make that a black dot. And then down 3, 1, somewhere down around here. Is that what yours looks like? That would be 4, 7, negative 3. Okay. Not so bad. You'll have to do a graph. You'll have to graph something on. Yeah, it's the Y. You're going right. You just have to train your mind because just think of these parts that are showing are the positive, and behind them would be the negative. Okay, going that way or whatever. Okay, did you get it? Okay. All right. Now, the region of three-dimensional space where all coordinates are positives, so that's that little part we've been looking at right in there, is called the first octant. First octant. So now you're going to need another one of your graphs because we're going to graph a plane. What's a plane? That's like that wall or the ceiling. It's a bunch of points that have come together and it's a space, okay? So we've got a plane. If we're going to graph 2x plus y plus z equals 6, if we just had two letters, that'd be a little different thing, but okay. So we need intercepts. So here's your process. You're going to find the intercepts. And if you want the x-intercept, what do? You let y and z be 0. And then solve 2x equals 6, so x has to be 3. And so that point would be 3, 0, 0. Then you let x and z be 0, and you get y is 6. And then you let x and y be 0, and you get z is 6. So you have these 3 points as the intercepts. So if I asked you to graph a plane, your process is going to be, I'm going to find the intercepts. And that means you'll have 3 points that look similar to this, remembering that here's your x, here's your y, here's your z. So then when we go to graph those, we graph those points just like we did where we were just practicing. And so we had 3 on the x, 6 on the y, and 6 on the z, and then you connect those with a straight line. And so if you can imagine that that's covered in, like it's a piece of glass sitting there, that's the plane that you've graphed. That whole space, like if it were solid, it would just be sitting there. And that's the first octant part of that plane. It might go on and on, but this is the part. So you're going to graph the intercepts and you're going to connect the dots, okay? Questions on that one? Anybody? We good? Okay. Did you get it? Oh, you want me to move back up? That's good. Okay, so now what's different about this one? X plus z equals 6. There's no x, so that means it doesn't have an x-intercept. I mean y, sorry. It's Monday. Okay, so we have 0, 0, 6 and 6, 0, 0, and we have no y-intercept. So when we go to graph that, we have these two, and so that plane isn't going to hit on the y, so it's kind of shown that it's going on. This is just a part of it, and so it's like, I just kind of did it like a puzzle piece, but it doesn't have a y-intercept, okay? The plane is parallel, if you will, to the y-axis, although I don't think it looks that way. But
how come you drew out?
Because it's going on, but it's not, if we had a y-intercept, it would come down like this and go like this, but they're just going on forever, and they're not going to hit the y. It's going to be parallel to the y. If that y-axis was going this way, like slanted, and then your thing would be coming this way. Okay? I am not as good at looking at three-dimensional. I had an instructor for Cal 2 and Cal 3 that I think he could just see all of that. He would write on the board and draw wonderful things. If I don't have dots and lines that I can say draw a straight line, I'm horrible with that. So if you're bad at that, then seeing 3D may be a little bit more difficult for you. It was always hard for me. It was hard when I taught geometry because I would draw on the board and I think they were laughing at my pictures, but it's okay. We got through it. All right, any other questions about that? All right, let's look at a couple of other things. And this sheet is one that will be helpful to you on your homework. And it's on the, I think it's on the printed notes. Y'all that have them, did that one print out on the printed notes? Uh-huh. Okay. So I would definitely either go look at it on the computer or print this sheet because it's got 4 different things here. And these were drawn by a computer, and it's 3-dimensional surfaces. And so this one is a paraboloid. It kind of looks like a parabola, right? It's just that you've got several parabolas that kind of connected like a net, and so that's what you've got there. This one's called an ellipsoid. If you remember from either algebra or pre-cal, and maybe not, but x squared over a squared plus y squared over b squared equals 1 was the equation for an ellipse. And so it looks kind of like that, okay? And then you've got a hyperbolic paraboloid, and it's sometimes called a saddle. Can you see that it looks kind of like a saddle? And you're going to need to remember that when we get down to 17.3, because they're going to talk about a saddle point. This will be a good reference sheet. And here's the hyperboloid that is in 2 sheets, which looks more like a regular hyperbola. Remember, hyperbola does that. So you're kind of having to remember back to Algebra 2 or Pre-Cal when you had those. But these equations here may help you in some of that. So you want to keep note of those when you're doing your homework. Okay, so we've looked at that. And in the homework, that probably printed as well. The next page is just a blank graph. Is it, Lindsley? Okay, but you have the handout now. I've put the handout out there so you could print as many of those as you want. So let's look at the problems. Let's get these, because this is what we're going to have on Math Lab. Okay. All right, number 1 says find the value of the function f of xy equals 2x plus 9y minus 7. Find f of 4, negative 2. So all you're going to do is 2 times something plus 9 times something minus 7. And we're plugging in 4 for the x and negative 2 for the y. And what do we get? Yeah. Not bad. Just plugging in. Should not be difficult. All right. For the next one, we're going to do 4 values, and here is the function. So you're going to be doing, here's your function if you want to write that down if you don't have the notes. And then we'll do these 4, and I'm going to scroll down so that I have room to work, but I'll let you write down the actual function first. So here's these that we're going to do. Okay? All right, so we're going to move down here. Okay, so we had the square root of 5y squared plus 4x squared, and we're to find f of 5, negative 5. So we're going to plug in. plugging in 5 here and negative 5 here. Okay. All right, so does it matter when you're squaring whether it's going to be positive? Positive and negative are both going to end up. So we have 5 times 25 plus 4 times 25. And what's the square root of 225? 15. So this is just algebraic, actually almost arithmetic at this point. So we're going to do the others. F of negative 1, 4. And you can go on and do that. I will write it up here. Now, Math Lab is not going to want you to put that in your calculator and give a decimal number. It's going to want you to simplify it. And so you want to think about, is there a perfect square in 84? Your choices, you want to think about the perfect squares. It's 4, 9, 16, 25. So out of those first small ones, 4 goes into that, and you're left with 21. So that's 2 square roots of 21, and that would be your answer. Yeah, you want, when you're trying to simplify a radical, you want to break it down into 2 factors. And there's lots of choices sometimes, but the only one that's going to help you is if it's a perfect square. And so you choose from 4, 9, 16, 25, 36, 49, those. And we kind of knew it had to be a smaller one. And if there's not one, then you leave it as square root. If that was 83, it'd be the square root of 83. You'd just leave it that way. All right. So then we're doing f of negative 4, negative 4. And we've got I left out a little step, but I think you'll get it. Okay. And the last one was f of 0, 6. Okay, so, whoops. I don't know why I was still in red. So for 180, what are we going to get? How are we going to break 180 down? Nine will go into it and would leave you 20, but within 20, is there another perfect square? 4, so 9 times 4 is 36. So when you break that one down, and that's what happens sometimes, you'll try one, and whatever you're left with, you say, oh, there's another perfect square in there. Yeah. So 5 is the one that's not perfect. You want to put the perfect square on the left. At least this is the way I teach it. If you learned a different way, that's fine. So ultimately, there's our answer.
I remember learning that. I mean, teachers taught
Uh-huh.
I never learned it.
Is this weird?
I learned it now.
Oh, okay.
I was wondering what was so hard about it.
Oh.
Most teachers, when they taught it back then, they just would confuse the heck out of things.
Oh, okay. So now it's good? It's never too late for it to be good. Never. When in 311, I think Math 311, and even in college algebra, when I review it, that's how I do it. And I always have them break it down and put the perfect one on the left and the other one. And I do the same with imaginary numbers when you're trying to bring those out, because it just simplifies to the right answer. So it is good. And with Math Lab, a lot of times in work, you're not going to leave it as 6 square roots of 5. You're going to have a decimal. But on Math Lab or a lot of testing, you would have to have the radical. So I'm glad that's good now. All right, so let's kind of go back and see where we were up here. All right. This one did not print when I printed the notes, but it says graph the first octant portion of the plane 4y plus 3z equals 12. And so let's see, what did I have down here? This is the way it comes up. Let me make this a little bit smaller. Okay, this is the way it comes up in Math Lab. Like, you're not going to actually be graphing it. But what do we know? Here's the process that I'd like you to think about. Up here, we're going to have, which one are we not going to have an intercept on it? No x-intercept. So it should hit on the y, and it should hit on the z. So if you're looking at this one, it's this and this. Yeah, you're right, Haley. And here, it hit here and didn't have a z. But here, we have a y one, we have a z one. Doesn't hit evenly on the x. So that's how you could tell which one of these it would be. Does that make sense? Because you're not actually going to be doing the graphing. You will be doing the graphing on the test in class, but on Math Lab, this is how you could go about. So this would be this one. Questions so far? Okay, then last one's a little bit crazy. Yeah. Yeah. Okay. If you go on Math Lab and you say, show me an example, it's going to be very, very detailed. You're trying to find trace points and you're doing this. I think we can circumvent all of that and really use just logic here. If you go back to your notes where, let's see if we go back here. You guys don't, some of you have it printed, but not that one. It's this one, and so we had x squared plus y squared, and we don't have a z squared. We have two variables with the squares, right? So if we go back, we have two things squared, z is not squared. So that's going to give you your hint that this is the thing that we're looking at. This was a cone. We didn't even have one quite like that. That's a sphere.
Even though it has,
Well,
x squared over 25, that would automatically.
it would be like, think about, that would make you think ellipse, but think of it maybe this way. 1/25 x squared and 1/25 y squared. Do those make you think parabola? Y equals x squared. And so you've got, if you look here, the z's going up this way, but you've actually got a parabola on the y and a parabola on the x, and we don't have a parabola on the z. It's hard to see, but I think if you'll kind of use that idea that there wasn't all three of them squared, that's going to help you with that one. Okay, just kind of use that. Right, yes, yes. All right, let's see if we can think about this one. we have 7x equals z squared minus y squared. Now, that's different because now we don't have plus. And minus might make you think about the hyperbola, because that was the difference in algebra between the ellipse was always x squared plus y squared and equals 1. It was a plus. And for hyperbola, there was a subtraction. So let's kind of look at this and go back to the 3D surfaces and see. What's the difference between these two? Because they're both hyperboloid, kind of. Does it look kind of like this one? Z equals x squared minus y squared? Okay, so let's z equal, well, it's one variable equals the other two squared and subtracted. Doesn't have to be z equals. So this one. And the difference between, if you think about it, the one on the sheet that I gave you or that I've shown you has the saddle going a different way. But because this one is x equals z squared minus y squared, it's going to be up the other direction. So, okay. And how about this one? 49x squared plus 9y squared plus z squared equals 441. What do you think? You think it's A? Or who said? Somebody said ellipse, I think. No? Let's go back and look. Okay, all three are squared there. All three are squared there, but what's the difference? Yeah, this one has some minuses, which is going to make it split. This one, they're all positive, so we're looking there. All right, so let's look back at our stuff. So it should be B. A sphere, which that's what that is, circles, what should be true about the x squared, y squared, and z squares? Aren't they going to be all the same numbers? Yeah. So that's going to be the difference there. C is that thing that split that had two minuses in it.
So those are split.
Yeah. Yeah. They look like they're sitting on top of each other, but they are opposite going. Okay, so that's a real simplistic way to do that. Again, if you go to the Help Me Solve This, you're going to see a whole lot of stuff that we didn't really talk about. I just wanted you, I'm not real interested at this point in you doing all that solving. I'm interested in you being exposed to the pictures and kind of looking at and kind of just analyzing a little bit. Does that make sense? Okay, so all of that is on MathLab and be able to do that. All right.